So this morning, we'll be looking at the rational method. So the rational method, like I said previously, is one method of stormwater design that has stood the test of time. So let's assuming that I'm being given a layout. This is a layout. And this layout is characterized, is 75 hectares, yes. And is discretized into catchment A, catchment B, catchment C, with their respective sizes. So catchment A is 15 hectares, catchment B is 5 hectares, catchment C is 14 hectares, catchment D is 9 hectares, and so on and so forth. Okay, so this is the work I'm giving. I'm asked to design what is the pipe sizes in each of the pipe in terms of the sewer and also in terms of the stormwater. So we'll start with the sewer. So let's assume there are houses now connected to this pipe. Okay, let's say there are maybe 100 houses or 200 houses. We don't care. But this is the main. This is the main collector pipe. This is the primary pipe that is going to deliver the final sewer to the treatment plant located at 4. So it means all the sewer will flow from here, some will flow from here, some will flow from here. Like I said, this is like the main. The tributary, the secondary pipe and the tertiary pipes are not shown. We don't need them. Like we said in stormwater, your job as an engineer is to design the main pipe very well. Once you design the main pipe very well, the connecting pipes, the tertiary pipe and the secondary pipes are no issue. But if you make mistake in the primary pipe, your problem has started. That's just the point. So the main pipe should be, maybe this main pipe might probably be 300 mm, 450 mm, or 250 mm. The minimum is 150 mm. Okay, in 50 mm. It is when, and then when it is getting towards the treatment plant, of course, it will become maybe 600, 500, or whatever, depending on the discharge, depending on the population equivalent. Okay, remember what I said last week? Sewer are designed based on garbage, what goes in is what goes out. So you use the drinking water parameters to design your sewer systems. At the end of the day, when they say what is the flow simply means the total population multiplied by the design parameter per capita per day. Depending on whether you are using individual population equivalent or you are using land use. Land use simply means how many people are anticipating per hectare, per area. You now multiply it because it's a virgin land. And that is why in district planning, we need to know the kind of number of floors or the kind of high-rise, the kind of population density we need, because it helps in the planning process. It helps in the design of the infrastructure. So this is very, very key. Okay? Very, very, very key. Okay, so now, what you do, a common sense of an engineer, catchment A is going to flow into catchment B. Catchment C is going to flow to catchment B, and together they'll flow into catchment D. Then catchment E will meet them at catchment D. Catchment E, sorry, will meet them at catchment D. They'll flow to catchment F, and then catchment G will come in, combine with them, and then they flow. So that's why as you are increasing, getting towards the outfall or entry point of the treatment plant, the pipe sizes are naturally going to be bigger than what you have upstream. It's because it's by aggregation. As you're moving downstream, you are aggregating. So, but before we start that, we need to lay some basic parameter there. So the pipe of catchment A is flowing from point 2.3 to 2.1. Remember, the survey will give you these points, right? And the length of that pipe is 500 meters. And the slope is 1:200. All of us know what it means. 1/200. It's 0.005. Then catchment B has a length of 250 meters. And this is the slope of the pipe. All of us know that we need the slope of the pipe so that when we go to our pipe sizing, we use the discharge and the slope to determine the length of the pipe. Everything that we did in our water reticulation applies in sewer and stormwater. It is about, what do you call it again? The basic law of thermodynamics. Okay, area multiplied by discharge is equal to area 1 plus area 2 plus area 3, and so on and so forth. It's simply what it is. Okay, so these are the different sizes of the hectares. So let's do the catchment characterization. Okay, so here we discover that the places is made up of 12% streets, 20% of roof. This 20% of roof should tell you that this is 20% house. So built up area is 20%. No, not 20%, sorry. Built up area is 32 to 37%. That's what it means, because this is streets. Okay, this is roof. So roof is houses. So you can see that this place is about, let's say, approximately 35% built up, because garden and parks is 63. So, and these are the equivalent coefficient of runoff, which is for stormwater. These are the equivalent coefficient of runoff. So we'll use mean weighted formula to be able to get the mean coefficient, because gardens and park has a coefficient of 0.1, right? While streets and roof have coefficient of 0.9. So we must find a way to find the mean, but mean is not enough. So we use what we call mean weighted average, and then you can Google that later on. Let it not distract us for now. Like I said, all you simply need to do is to multiply this by this. Maybe I have to do that. If you want to get, let me demonstrate it so that quite understand, because it's going to be a take for somebody who will be wondering what I've been hearing about mean weighted average. What does it really means? So let me just demonstrate it now so that somebody will get it. So just hold on. So I'm going to multiply this by this, this by this, this by this, and then divide by the total of 100%. In other words, what it does is that it will capture the weight. So in this case, this 0.1 will be influenced by the weight of this. Because if you check the mean, okay, let us take the mean of this. Let's take the mean. For instance, we have gardens. Garden is 0.1. We have streets, 0.9. We have roof, 0.95. Just watch me. Then we have others. Others is 5%. Okay, and roof is 20%. This is going to take our time, but I think it's the learning curve. Street still 12%, and 63% is the gardens, and the roof is 5%, and it's 0.2, and that's 5%. So if somebody says you to take the mean, all of us know what the mean is. Normally, the mean, let me increase this font size, please. So normally the mean, watch this, mean, normal mean, average, mean or average. Somebody say, oh, let me just take the average. It is not always the case. It is not accurate. So average will be 0.1 plus, okay, 0.9 plus 0.95 plus 0.2. So now let's take the average. So the average will be, just hold on. This is very, very elucidating so that you know what we mean by mean weighted average, which is the limitation of using normal mean. So this is plus 0.1 plus 0.9 plus 0.95 plus 0.2. The answer is 2.15 divided by what? 4. Divided by 4. It's giving us 0.54. So the average of this value is 0.54. But if you're using the mean weighted average, watch me now. The mean weighted average will tell you it's going to be 0.1 times 63 plus 0.9 times 12 plus 0.95 times 20 plus 0.2 times 5. All divide by what? 100. Yes. So let's go now. So it will now be 0.1 times 63 plus 0.9 times 12 plus 0.95 times 20 plus 0.2 times 5. It will give you 37.1 divided by 100, which will give you what? 0.37. Gentlemen, take a look at mean weighted average and normal average. This one is called weighted average. That's just the word, whether you put mean before it or not. This is called weighted average. Why the other one is normal mean, normal average. Can you see the difference? So tomorrow, if somebody says, oh, the catchment value here is 0.1, here is 0.9, just take the average. No, it's not accurate. It is not accurate. You need to look at the weights. You need to factor the weights attached to each, because it's like you have 100 naira and I have 20 naira. The average is 120. But when you have 100 naira and you are spending 80 and I have 20, I'm spending 5, the is not right to take average. So this is just what it means. And I hope this is able to add this must be a new thing for some of us, but it's quite new. So the weighted average of the whole catchment now is 0.35. That's just the point I'm trying to make. Okay, so here is it. So the mean weighted average of the whole catchment is now 0.37. But if you use normal average, you go to 0.54. So I think that is that. Then for the storm, when we're doing the storm, we're going to use 10 minutes. And because it's a virgin land, we are assuming that we have 100 capita per hectare, 100 persons per hectare. That's what it means. So if you look at it, you know, this is just planning value, or what do you call it again? Not just planning value, but land use. Yeah, that's the word. This is land use value. It says we are expecting that 100 people will be in every 1 hectare, meaning 1 hectare is 10,000 square meters. So what this thing means, we're expecting 10 people every 1,000 square meter. That's what it means. 10 people every square meter. So you now imagine what can be 1,000 square meter. That's probably a 4-bedroom duplex, whatever. Okay, and it's going to be a bungalow, because if you go up, it might be probably be 20 people. All right. Then for water consumption, we are assuming that the water consumption per person is 130 liters per capita per day. And we are using a peak factor. Peak factor is just like saying safety factor. And that is for the sewer. For this, remember, for the storm, when we did water reticulation, we also have a safety factor. In fact, every engineering design comes with a safety factor. But in this case, we don't call it safety factor, we call it peak factor. Okay. And sometimes we also say peak runoff. What we're trying to say is the most critical worst case scenario. All of us know what safety factor means. Then we have what we call parasite water. This parasite water is to introduce contingencies. Sometimes we say, yes, what water board gives you is what the treatment plant will treat. Sometimes it's not often the case, because sometimes we go out there, we also buy water, or we get extra water. Even if we don't get extra water, during storm events, our pipe will leak and water will enter our sewer line. So we need to put in some level of extra second layer safety factor. Okay. Then the quality of pipe we're using a pipe of roughness of 1.5. That should tell you that that's a concrete pipe, if you remember what we did last time. Okay. So we now said The choice of sizing your pipe depends on your discharge, your slope, and the roughness. So roughness is default. Am I using a PVC pipe? Am I using an iron pipe, a steel pipe? Am I using a concrete pipe? So that one is already set. Then the slope, we know the slope. Once the surveyor has taken his design, slope will pop out on its own. Then the discharge is what we are going to do. So in all these three parameters, two are almost known. One is unknown. And when we get this one, we use this value here, and then we get our pipe size. Remember, the whole output of our design is simply to say what size of pipe are we going to use. That's just what it is. When we say we are designing any pipe system, it's just what size of pipe do I need that can safely convey my runoff, my sewer, or my drinking water, or my potable water. That's just what it is. Okay, so we said, okay, that's that for now. Then for the sewer again, because this place is an unbuilt area, so we need to decide what we call dry weather flow. I say what dry weather flow is the flow when there's no storm event. In a layman's language, dry weather flow means the flow when there is no storm water event. And how do you calculate your dry weather flow? It is simply the wastewater flow per person or per capita multiplied by the population density, PD, multiplied by the safety factor, multiplied by, and then you add, sorry, not multiply now, you add the parasite water or the filtration or the second tier safety factor. There's only safety factor in our design. Engineering, I tell people, is a science of approximation. Nobody is sure of anything. If you say this column will carry a weight of 400 kilonewton, it is not perfect, it's not static. It could be 380, it could be 420, it could even be 450. But at least reasonable assumption and common sense must apply. So here, we said that the drinking water requirement per person is 130. So we multiply by the hectare. Now, this can be confusing for some of us, but hold on, let me just explain to you. This is 130 liters per capita per day. You multiply it by 100 persons per hectare. But you now convert day into seconds, like we did in water reticulation. That is why we divide by 8,600. This 8,600 simply means 60 times 60 times 24. That's what it is. 60 times 60 times 24. In order to convert day into seconds, then you multiply by safety factor of 2, then you add infiltration water of 0.1 for every 0.1 liters per second for every hectare. So at the end of the day, the wastewater flow per hectare is 0.4 liters per second. What this simply means is that for every 1 hectare and in every 1 second, you're going to have 0.4 liters of wastewater flowing from houses, from their toilets, from their kitchen, wastewater. Remember, not stormwater in this case, not stormwater. When it comes to stormwater, we are using precipitation values. So for now, we're talking about, for this first one, we're talking about sewer. So I hope there's no question, but if there's a question, I'm ready to answer this question, because it's key for you to understand what is the wastewater flow per unit hectare. Then you now have to multiply by all the hectares. It will give you the exact value. Please, what's the question, sir? You have a question? You can unmute yourself. Okay, maybe I didn't hear well. Okay, now when you come to stormwater, how do you calculate the stormwater? The stormwater is the maximum runoff. We'll call it runoff this time. We'll call it runoff this time. Maximum runoff is now the rainfall intensity multiplied by the area of impervious. The rainfall intensity, in other words, the rain that is falling multiplied by the, so you multiply the rainfall intensity multiplied by the area contributing to runoff. And the only area that contributes to runoff is the impervious area. It's impervious area that contributes to runoff. Okay? Then if you break it down, how do you get the impervious area? The impervious area is simply the total catchment area multiplied by the peak runoff coefficient. Let me say it again. The peak runoff coefficient multiplied by the total catchment will give you the area of impervious. So in other words, what happened here is that I broke this one down into two parameters. Gentlemen, if I come to your house, for instance, and the area of your house within your compound is 40%, the area you built, the built-up area, including the interlock area anyway, is 40%. It means your runoff coefficient is 0.4. Because the other area that is green area does not contribute to runoff. I will assume, no, not that they don't contribute to runoff, but they contribute 0.1, they contribute 10%. But your built up, your footprint of your building contributes 95% of runoff. All the water that falls, they don't penetrate into your house, they don't penetrate into the roof, they all flow into the external drain. So it means the runoff of your house is 0.4, 0.5, because the green area do contribute to runoff, but minimum runoff is assumed that they percolate. That's why in those days, when you bring your drawing for approval, where things are working normally, they will ask you to go and redesign and make provision for green areas. The idea is that we want to keep the runoff coefficient as low as possible, because the runoff coefficient is a factor of the area contributing to runoff. These are the areas contributing to runoff. So if I multiply the catchment area by the runoff coefficient, I will automatically get the area of imperviousness. So that area of imperviousness is more like the hard area, gentlemen. It's like the word impervious or paved. Either you call it paved area or you call it impervious. The impervious area or the paved area is the area contributing to runoff. So that is the area I will multiply by the value of the rainfall intensity. And this rainfall intensity must be a function of duration and frequency. So when I go to my IDF curve, I'm going to find the appropriate duration of rain and the frequency of the rain. Remember, we have 5 years, we have 1 year, 5 years, 10 years, 25 years, 50 years, 100 years rain. That is the frequency. You don't just use 25 rain or 20 rain. No, it depends on what you are, the level of factor of safety you are designing for. Whether you are designing for storm, you are designing for flood, or you are designing for normal runoff. Normal runoff means 1-2 years. It's a rain that comes once every year. The maximum rain that comes once every year. 5 years means the maximum rain that comes once every 5 years. Then 10 years means the rain that comes once at least every 10 years. So that becomes my reference. Remember, the higher the safety factor, the higher the frequency, the higher your design, your sizing, your component sizing. So that's why you must not use a too much high safety factor. You must not use too much low. That means you need to know what you're designing for. Okay, so I think everything is clear. So now we've established how to calculate for dry weather flow, which is for sewer. And we've also established how to calculate for stormwater, which is for runoff. So I think the next thing now is for us to say, yes, this is for runoff. Now, how do you calculate rain intensity? And then how do you choose the duration and the frequency? So this table gives you an idea. It says if you are designing for storm and the place is a rural area, simply use a design storm of 1 year. If you are designing for a surcharge, against surcharge, in other words, it can surcharge and it can go down. You use 2 years. Then if you are designing to resist flooding, you use 10 years. It comes again, it says if you are designing for residential area, you use 2 years as your return period. If you are designing for storm means normal rain, normal gutter, in quotes, local balance, normal gutter, normal drain of your house. in a residential area, you should use a design period of 2 years. In other words, it's saying that you should use that maximum rain that occurs once every 2 years. That must come at least every 2 years. There are some areas in Abuja, every 5 years there'll be flooding. So when you are asked to design for a place like that, it is that 5-year flood that you use. Because it's not every year that those maximum rain comes. But like you know, every year it rains. So there's a default frequency rain that comes every year. So you use the one for every 2 years. But if you're designing against surcharge, you use 3 years. Then if you are to design against flooding, in other words, it must never flood. It must never flood. If that is your design criteria, then you have to use a 20-year flood. Then if the place are city centers, the recommendation is that you should use 2 years or 5 years return period, or 2 or 5 years rain. We're talking about city centers. Why is it so? Because city centers have higher insurance value. City center has higher insurance value. And if you're designing against surcharge, you use 5 years. If you're designing against flooding, you use 30 years. Why are we using 30 years? Because it must, okay, not now. It must never flood. It's a high risk if the city center floods. Then if you are designing underground railways and you are designing for normal storm, it says you should use a 10-year return period. And for surcharge, more than 10 years. Then for flooding, you should use 50 years. The question is, why will I use a 50 years rain for underground railway? Because it's a crime. It's a disaster for underground to flood. It's a complete disaster that subway systems is flooded. Because once they flood, the losses, the colossal loss, the insurance payment is so high that it will be unbearable. That's why securing underground infrastructure is very key. Because imagine when it floods underground, the whole electrical devices, the whole sensors, everything I've invested on underground. In fact, it could even submerge. It could submerge, and there could be what do you call it? Subsidence that the whole place will collapse. So underground systems must not flood. So hence, we increase the safety factor to about 50 years. Yes, you can call these things, like these things represent more of safety factors. But those safety factors will now apply the type of rain we are going to use to design your runoff. Okay. That's why for those of us who stay in Abuja, if you come to central areas, you see that, like I always tell people, it will never flood in central area. If you see what Julabega did there, you see the big, huge underground systems, underground pipes, concrete underground pipes, big manholes. Why? Because this is the city center. So it's not for, you can't allow flooding, because when flooding occurs, the insurance payment is so high and losses is so massive. So this is a typical of a intensity, duration, frequency curve. Intensity, duration, frequency curve. Somebody is raising his hands. Abayomi, what's the question, sir?
Thank you for this point. I want to ask, just from your understanding, flooding occurred in Dubai, was it last year or 2 years?
Yes.
And what could have been the cause in terms of design with what you have just explained?
Well, I think it's part of climate change, number one. And it's part of, if you remember, it's been more than 20 years. We've never had that flooding occurs. So probably their systems were designed for 5, 10 years. What is 20 years? I think that flood that occurs in Dubai is about 50 years. Design, just like the one that occurred in Lokoja in Nigeria, 2012. How many of us remember 2012? Was it July? July 2012, I said it last time, that was a 50-year flood that hit us. Since 2012, have you heard of such a flooding again in Lokoja? Lokoja was on lockdown for like 1 month. River Niger, the confluence of River Niger in Lokoja was on lockdown for 2-3 weeks, let me not say it. Okay? And Bayelsa was submerged. Bayelsa was completely submerged. People who are old enough will attest, were able to attest that the last time that kind of flooding happened was 50 years ago. So you see, we couldn't design our system for 50 years. So Dubai, they didn't see it coming. They didn't see it coming, and they couldn't design for more than maybe 25, 30, 50 years. So that's kind of flawed. It's bound to happen. But once Germany suffered their own in 2016, remember, a city in Germany was submerged, and when they checked, it was a 100-year flood that hit them. They said the last time they experienced this flood, because when it happened 100 years ago, they were able to mark it. They went to their flood gauge station and they mark where the height of flood was. And when they measured what happened again, it was exactly what happened to them 100 years ago. For want of time, I would have Googled it and you see it. So in terms of design, Dubai didn't anticipate that kind of 30, 50 years flood. So their system we are designed for maybe 10 years, 15 years, 20 years. But if 50 years flood comes, of course, it will be matched. But I can tell you they might not experience it again in the next 5, 10, 20 years. But in the next 50 years, nobody's sure of anything. I don't know if that answers your question.
Yeah, it does answer. And in that case, once it comes...
Let me also say this. You don't go on designing for 50 years. If you design for 50 years, the cost of construction, the cost of implementation will be so high that somebody will think you are stupid, in quotes. That's why, I mean, we can't help it. We can only design for 10 years, 20 years, 5 years. Then if it is normal drain, 1 or 2 years, depending on whether it's a rural area, residential area, or city center. So for me, 1 to 5 years is enough. If you ask me to do a design in big cities in Nigeria, I'm not going to do more than 5, 10 years. If 20 years come, I'm sorry. Let's enjoy it. Except we have underground systems, or we have very special systems where there are banks, where there are underground systems, tunnels, and what have you. Thank you. Okay.
Sorry, sir. When we have a scenario in Lagos that happened, I can't forget that day. July 15, 2021.
Okay.
It rains. I'm not sure I've seen that level of rain for quite a long time.
Yes.
It rained heavily from the morning till evening, and everywhere was flooded.
Mm-hmm.
So now, if you say we don't design for such kind of thing, we always live by it. We know Lagos is a waterlogged area in some areas, and we now have that level of intensity, high intensity from the beginning to the end of that day.
Yes, I remember it. I remember it. Lekki was flood. I know that date. Right, go ahead.
Yeah. So I can't forget that day. So now,
yes,
what I'm trying to say is this: if as a designer you don't factor that frequency or that number time in your design, which means at any time that such thing occur, we all live by it. After some days, it's
that is yeah. Go ahead.
So
that's my opinion.
I've stopped now.
Okay, that's my perspective, sir. That's my perspective. The only place I know, and I always boast about it, is a country like Germany. Germany designed their dams for 100 years. That's why if you see the dams, you begin to wonder. Sometimes their dams can be 50, 30%. They give overboard of 5 meters because they value risk. But that one that happened in 2016 took them by surprise. It was 100 years. Or maybe more than 100 years, because why I say 100 years, because the last time it happened was 100 years. This is a very beautiful question, but that goes to show how designers are limited by just opposing cost and design. Let me tell you, for instance, sir, I told somebody that I want to use 2.5 mm wire to pipe something for a pump, a 1.5 horsepower pump. The person said I should use 4 mm. Why? Because tomorrow the pump size might change, the type of pump might change to 2.5 horsepower. And then my 1.5 will not do. So I was already calculating the cost of buying a 1.5 wire, 2.5 wire and 4 mm wire. So I can decide to risk it and say, no, give me 2.5 because I don't have money. And I believe we're not going to choose 2.5 horsepower any day. But then tomorrow they might decide to increase the pump to 3 and operate them at the same time. So you see that cost will always have an impact on your design philosophy. I don't know if that's practical enough, but that is what it is. And that is why you as a designer, You must balance the two.
Thank you.
All
Thank
right.
you.
I would like to contribute to this, if you don't mind.
That of Lagos. Okay, let me say it before you contribute. That of Lagos, I think Lekki, based on what we know today of Lekki, if they know what they know about Lekki today, that they price Banana Island and Lekki, if they know what insurance value of houses there will be today, they would have designed for a higher frequency. That's just it. That's just it. So go ahead with your question.
All right. So I think while discussing about drainage structure, I think it's very important for us to differentiate between different kinds of hydraulic structures.
Okay.
Now, you said something about Germany designing their dam to 100 years return period. Yeah, that's correct. That's a very major hydraulic structure. Dams, which other ones? All those big hydraulic
Transmission pipes.
structures.
Transmission pipes. Transmission pipes.
Exactly.
Transmission from river to treatment plant. Thank you.
All right. So the point I even want to raise is when you're talking about small hydraulic structure,
Yeah, 1, 2
it's
years.
it's not appropriate for us to use something like that, 50 years, 100 years. You use a
Of course.
smaller
Yes.
design period, such as
Yes.
10 years return period for our drainage structures.
10 is too much. 10 is even too much. Go ahead.
Yeah. For our drainage structures, it is advisable that you use 10 years return period. Now, somebody talked about the rainfall event that happened July some months ago. Now, the flooding
Days
events
ago.
in
Yes.
Lagos is a very special case because Lagos is a very developed area, unlike most of other cities that
Thank
the
you.
development there, you're having infiltration happening everywhere, but here
Yeah.
everywhere is paved.
You paved.
You get so you
High
cannot
runoff.
because of that kind of rainfall event, let's say a rainfall event that happens in once in 50 years, you're not going to design your
No.
drainage system to be 50 years. That's going to
No
be
way.
exactly. So I think it's something
It's
that you have
unbuildable.
to.
It can't be. Governor will not. The governor will even fling itself. The government will fling it off. The another thing we
Exactly.
must realize is that Lagos, the rainfall intensity of Lagos is 140 minimum. Other areas are 80, 100. So already Lagos has a high precipitation value, a high storm event. That's even number one. That is number one. Meanwhile, let me also say this. It is not the duration of the rain that causes flooding. No. It is the initial intensity within the first 10, 15 minutes, remember. So most times you can see rain will rain from Lagos from morning to night. You won't see flooding. The one that will cause flooding, after 15 minutes, we'll find out. You know, after 15 minutes, it's already giving you 140 on your own
Yeah,
gauge.
flash flooding.
Flash flood. So once you declare 140 within 10 minutes, your early warning system, which we don't have anyway, you ring alarm. There was a flooding that happened in the US last week. You know the mistake they made? It was just to signal those. People perish. More than 100 people died. All of us, you will remember, was it 2 months ago? What killed them was to sound alarm. Within 10, 15 minutes, they recorded very high value upstream of that city. For reasons I don't know, as developed as America is, they could not inform those people downstream on time. And within 2 hours, the rain moved to inundate. When it goes to that place, which is a flat area, flat plain, it rose to 30 meters. And the devastating impact is those children that perish for nothing.
Yeah.
I watched it and I saw where information communication, the resources are there. Even in Nigeria, gentlemen, let me tell you, before Lagos will flood or Bayelsa or Lokoja, we already know in Kebbi State too. Once we measure in Kebbi State, upstream, remember River Niger, that is the source of the hot flooding because it's a 9-country riparian community. Once we notice in Kebbi that the height of water there have exceeded limit, it means before it will get to Lokoja, if the height is giving us 5 meters.
And then, can I make an observation, please? Hi. Can I make an observation, please?
Go ahead, sir. Since he's not talking, go ahead. We are with you.
KB, up 15, 20 meters high, and that's already disaster. So it's very, very, no question. Okay, so let's move on. So this is the frequency rate intensity curve. So if you are reading, you see 1 year. Let's say after 6 minutes, 1 year is 5. You find out that, okay, I will use Nigerian own. This is European own. This is German own. Okay, I think I've explained this before. This place simply tell you that before you get runoff, there will be drifting, there will be wetting, there will be evapotranspiration, there will be infiltration. What this diagram is trying to demonstrate to you is that before runoff could take place, or out of all the rain that falls, 100% rain that falls, runoff is just a small percentage. And it occurs over time. As you move towards duration, it percolates, it moves. I'll still explain this further. This chart now shows you the impact of the slope on and the paved area. Here is the paved area. And then your how you choose your D. For me, and from experience, just choose 10 minutes. It's okay. Here it's just telling you that if the slope of the area is more than 4% and the paved area is less than 50%, still choose 10 minutes. But if the slope is more than 4% and the paved area is greater than 50%, you should use 5 minutes rain should be your trigger. But for me, based on new development, 10 minutes is enough. Just go to the chart, read it up at 10 minutes. So here is trying to explain to you the impact of time. Why do we choose 10 minutes? It is because to get maximum flow, travel time must be equal to time of rainfall. It's a technical thing. But what it simply means is that if, I don't know how to explain it, but if rain falls at point A and it travels for more than 10 minutes, the accuracy goes down. But if exactly it travels within 10 minutes, then we expect it to generate maximum runoff. So what happened is that in the course of this training, I'll explain further on that. So I'll explain further on that, please. Now, here it says that the average rainfall in Germany, which is also applicable in some areas, in some cities, for a 10 minutes rain and 1 year frequency. That's why you see this arrow 10-1. Simply means the rainfall intensity after 10 minutes at frequency of 1, which simply means normal storm. Normal storm is about 126.3 liters per seconds per hectare. Let me quickly go to our design code, which I shared with us last time. And let me go to, I don't know which city I will go to now, but let me use one of the cities. Good. So let me use like, what city is this? Lagos Island. Oh, Lagos. This is Lagos Island. Like I said, this thing was an issue for designers until the Federal Ministry of Works 6 years ago came up with this standard design chart. So you don't have to go and start asking River Basin or asking people, what is the place this? No, you have it now, standardized, right? Which is a very commendable thing that did this, and it's so wonderful. So now, let's say I'm using a 10 minutes rain. This is my 10 minutes. I don't want this assistance. Why are you disturbing me?
Sorry, engineer, can I ask
Yes?
a question?
Go ahead, please.
My question is this. At the time we're articulating what return period and year vis-a-vis the anticipated flood we want to consider for an area. And just like you explained, we have this probability concept in this design. You've said exactly. 1 in 30 years, 1 in 5 years. You might finish that one in 30 years now. and the rain comes the next day. The flood comes, it hits you. That is it. But the impact of it, like you said, insurance cost and co, is what you suggest is what we will have to consider in
Exactly.
knowing what decision to take, because that's the dicey area. If we finish
Yes.
our design today and it comes tomorrow, hey, what happens? If it doesn't come, fine, because the probability may come or it may not come. So how do we match that insurance? And that's my own. I'm just thinking of
Well, that's a good question. That is where an engineer, that's why a consultant is a consultant. Let me just give an instance. If you ask me to design a flood system for Abuja and Enugu, no, Enugu is good. Let me say, with all due respect, let's say Ebonyi State. Ebonyi State is a rural area. No, sorry, it's a agrarian area. Most of the place, except for Abakaliki, it's an agrarian area. So, what is the impact of flooding in Abuja, Gariki, Wuse, and the impact of flooding in a place like, say, Afibo in Ebonyi State? I can use 1 or 2 years for Ebonyi State, or even 1. What is 2? Because if it floods, my engineer, is farmland that will flood now.
Yes, it is. But when you have
no insurance cover, I mean, it's farmland or bungalows. But when it floods in Wuse, Gariki, or Lekki and Ikoyi, I mean,
a lot of insurance.
Yes, disaster. So that's what it is. And one thing I've always said is this: I said, this is our profession, this is our engineering profession. It's a science of approximation.
Yes, nothing is.
You assume reasonably. Nobody is sure of anything. Like I tell people, you say this column will carry a weight of 400 kilonewton. Who told you? It could be between 300 and 500.
That is it.
So reasonable assumption is a key thing. And also, you should be able to defend whatever assumption you are making. For instance, now, look at Lagos. A 10-year rate for Lagos at a return period of 1 is 100. At a return period of 5 years is 160. At a return period of 10 years is 180. Huh? At a return period of 25 years is 200.
Yes.
If you design with 200, if the person who is designing for 1 year is getting a drain size of 1.2 meter, I can bet you that your drain size will be 1.8 meters.
That's true.
Or whether you are designing for a retaining basin, a stormwater overflow, even a dam. I mean, this is cut across. Whatever the hydraulic structure, like one of our engineers said, whatever hydraulic structure you are deploying, this thing, whether it's a retaining basin, an overflow structure, a primary sedimentation tank for your treatment plant, all these things are factors. You know, in Nigeria, we don't treat stormwater, we don't have stormwater facilities. But in developing countries, they have different overflow structures because they don't want the city to overflow. Some places that are prone to flood, we have huge reservoir underground. So that when the flooding exceeds limits, they just open the underground infrastructure and the water will just flow there. Then after a while, they will do a control release. So this is our IDF here. So you see here, if it is 10, you use the value of 140, depending on what you are using. So this is just a demonstration of this. So like I said, you use between 10 to 15. Don't use more than 15. Okay? But most times 10 is a more higher safety. All right, so let's go back to this one. Remember, this is our storm. For Siwa, nothing like 10 years, 20 years. Rather, it is now value of the drinking water per capita per day, which also vary between 100 and 200. But in Nigeria, 100 is adequate. Some countries like the United States, they use a lot of water. So they have swimming pool, they have washing cars, they have agriculture, gardens, and everything. So their water requirement per capita is always on the high side. In Germany, they are using 120. Okay, let's go back and finish this. So here, how do you size? Number one, you choose a return frequency, which we have been discussing for the past 30 minutes. Then you estimate flow time, which we said empirically, nominally, use 10. Then you consult your IDF curve. You choose which appropriate rain intensity. Lokoja is about 120. Abuja is about 100 for a 1 year. When you start going for 5 years, you now start going maybe 120, 140. Most countries most states in the south, the 1 year return period is about 100, 120. Except Lagos, that is about 100 too. Bayelsa is around 120. If you start going up north, like Sokoto, if I go back to that chart, Sokoto is around 80, 70, 90, 70, 80, 90 for 1 year. If you start going to 5 years, 10 years, you start going 100, 120. Most states in the north don't even exceed 120. That's why the only place you hear about flooding in the north are those communities that are within the catchment of the River Niger, and it has to do with overflow of the banks. For me, that is what causes flooding. When overflow or dam break or dam overflow. But in places like Bayelsa, Port Harcourt, Lagos, you don't need dam break. You don't need overflow structure. Normal intensity rain will cause flooding for you because of high storm events. Okay. Then if you do that, you now choose your pipe size. Okay. Reminding you that pipe size depends on the discharge, the slope, and the roughness. So these are just the 5 basic steps to design your stormwater thing. And at that point, so to design for wastewater, we first of all design for catchment A. So catchment A, so go to your material. You see a material that says catchment calculation sewer. Please, can we open it? You see catchment calculation sewer. After sewer, we will now do catchment calculation storm. Open the file called catchment calculation sewer. So let's start with the sewer. Okay, so this is it. So to calculate our sewer network, we make assumption. Please open the PDF. My apology, please. My network went off. So open the PDF. Are you with me? So here, we assume that the drinking water requirement is 130 liters a day. The population equivalent is 100 capita. This capita simply means persons or whatever, it's just a technical word, per hectare. I've tried to explain this before. In terms of development, 1 hectare is 10,000 square meters. So if you divide both sides by 10, if you remove 1 0 from both sides, it means 10 persons per 1,000 square meter. 1,000 square area. That's just what this thing means. So if you see a place where a plot of land is 1,000, it means you don't have to build. We expect 10 people to live in 1,000. That's what it means. So then the peak factor is 2. big factor is 2, right? Then parasite water, based on the design code, is still 0.1. Okay. Now from the drawing, this is the drawing. So we start with catchment A. Follow me now. Okay, we have done this, the catchment characterization. So here, that's around 4 page. So for catchment A, the area is 15.3 hectares. Go with me. Therefore, the wastewater discharge per hectare. In engineering, we always do things per unit. What is the value per unit? If you are designing a slab or whatever, or a beam, what is the volume per meter length or per square area? So we always do unit. So that you now multiply the unit by the whole. So here our aim is to what is the wastewater flow per hectare. And that wastewater flow per hectare means the contribution of one person, which is 130, you are producing. Garbage in is garbage out. If I give you 1,000 liters of water for consumption per day, I expect you to produce wastewater that is also equivalent of 130 per day. So that's how I get my discharge to my treatment plant. So I multiply by the population equivalent, which is 100. Then multiply by safety factor, and then add the parasite water. It will give me 0.401. This value means this is the flow per hectare. But since we said that catchment A is 15 hectares, I will now multiply this 0.4 by the total hectare, and that will give me 6.29 liters per second. So this is the wastewater flow coming out from catchment A. My job is now to design a pipe that can convey this. So the next thing I have to do is to go to my nomogram, to go to my chart. Where's my chart? Remember our chart? You remember our monogram? I think we have it in module 1. It's the same. You can download thousands of them online. Thousands of them online. All you need to do is, any chart you are using, first of all, we're using PVC pipe, so I'll use 0.1. Well, we're designing sewer. Sewer is PVC pipe. Here we are. So I'll come here, I'll read 6. This is already coefficient of 0.1. So this is for PVC pipe, right? Then the slope, I'll check the slope. What slope is that? What slope is that catchment? The slope is 5%. Okay, let's assume the slope is in the chart anyway. Yeah. Yeah. The slope is somewhere here. On the table. This table. This is the slope on this table. Okay. The slope on this table says 1 is to 200. 1 is to 200, right? Which is 1 over 200. I don't know what 1 over 200 means. But if you check 1 over 200, for a distance of 500, it means 1 over 200 times 500. Okay, so it means, hold on, 1 divide 200. So the slope is 0.005. 0.005 is the slope. Then, if I now want to use this my chart, what does my chart says? My chart says I have to multiply it. If I now do it per 1,000, it means multiply by 1,000. That will give me 5 per 1,000. So when I come to this my chart, I'm going to read this value against 5. And here is 5. So I'll go to 6. I'll go up and stop at 5. What is it giving me? It's giving me 125 mm pipe. 125. If you go against chart, it's giving me 125. But I cannot use 125 because the code of standard for sewer design says that the minimum diameter of pipe for your sewer network must be 150 mm. Let me repeat it again. The standard design, both for Euro code, Indian code, British code, whatever code, all the code are the same. It's just small differences to have some level of independence or whatever. Says that if you're designing for a sewer network, that the minimum pipe size in your network or the minimum pipe size to be used is 150 or 6 inches pipe. So even though I got 150, 125, I am constrained to use minimum values or minimum recommended value, sorry. So that pipe size is 150. So it means the pipe for catchment A is 150. So this pipe must be 150 mm. Are we together? Good. I move out to catchment B. Catchment B, the same thing. 130 times 100 times 2 times 0.1, just the same value. Okay. As a matter of fact, this value is going to be constant. Okay. All I need to now do is to now multiply it by the so I will now multiply this value by the area of catchment B. So here, look at it here. So this is where I've done the whole calculation for us. So if you multiply A by 50, if you multiply the value you got, 0.4 by 15.63, you're going to get 6.25. If you now multiply, let me make it easy for us. Hold on. Sorry, 1 minute. 1 minute. I want to bring up something. Rational method. Okay. Now, good. Now, gentlemen, the value I just got now says 15.6 times 0.41. It will give me 6.26. So it means the wastewater flow for catchment A is 6.26. Now, for catchment B, I will multiply the catchment area by 0.4 again. It will give me 2.19. However, catchment B is the value of catchment A plus its own. If you multiply 5.47 multiplied by 0.4, which is our unit wastewater flow, it will give you 2.19. But the wastewater flow in catchment B is not 2.19. It has to be 6.26 plus 2.19, and that will give you 8.46. So the value for flow in catchment B now is 8.46. Why? Because it's taking the value of A plus its own value of 2.19. That will now give you a total of 4.86. If you go to catchment C, it's going to be 0.4, which is the unit flow, multiplied by 14. That will give you 5.64. Just similar like 6.64. If you look at catchment C and catchment A, they are almost the same, just that catchment A is a little bigger. So the wastewater flow in catchment A and the wastewater flow in catchment C are almost the same. However, this one will not add up to anything because there's no other pipe coming upstream. Therefore, the flow in catchment C remains the same flow as I have gotten because catchment C is going here. It is when we get to catchment D that I will now need to add the value of catchment B plus the value of catchment C. And that's what you're going to see in the subsequent page, which is what you now going to have here. So if you look at this place for catchment C, the value of catchment C remains 5.64. Please open this chart and go with me, please. Very important. Open this chart and flow with me. If not, you'll be confused. So catchment C remains 5.64. But when we get to catchment D has a area of 3.19. If you multiply 3.19 by 0.4, it will give you 1.457. But the aggregated flow there will now be the value of B plus the value of C plus its own value. Engineer, how do you mean? This is what I mean here. If you come to catchment D, gentlemen, the flow here is the value of C plus the value of B. The value of C plus the value of D, B for ball, will give you the value for D. That's what we have here. So the value of D is 8.46, which is value of B, plus the value of C, plus its own value. Yes, I need to add this. So if you add this, plus this, it will give you this. I expect a question there, except you can tell me that you understood it. Now, when we move to point E, the point E will just be what it is, because there's no upstream. It is supplying to the tributary of D. And that is why when you come to this chart, point E is 0.4 multiplied by 14.84, it will give you 5.95. And the total value of discharge in pipe E is still 5.95. But as soon as you go to point F, that value of point F becomes its own value plus the value of point E plus the value of point D. So point F, this is point F. Point F is now catchment F plus catchment D plus catchment E. And that value is what? 23.49. Do you see how the wastewater flow is increasing? For instance, let's design for catchment F. What is the pipe size in catchment F? Or let's start with D. Because I don't need to design for C. C will automatically be the pipe size of A. Remember? Those of you that are civil engineers, once you see a beam that is 4 meters and you see a beam that is 5 meters, nothing wrong in designing the same reinforcement for two of them, provided you use the one for 5 meter beam. That's how we make life easy for ourselves. I think mechanical people do the same thing. Okay, so if I design catchment D, which is 15.66, I will simply go to my rational chart. Where's my chart? 15 is somewhere here. Look at this is 10. This is 20. So 15 is this one. So I'll go up. Assuming they're the same slope, I'll end at 5. Here's 5. It's giving me 150 mm pipe. Okay? Exactly at 150 mm pipe. But when I get to catchment F, which is 23.5, and I go to my chart, and I go to 23.5, let's say half here, and still at 5%, is giving me, is in between 150 and 200. And what did we say last time? You choose the bigger of the two. So here I will choose 200 mm pipe. So while I will choose a 150 pipe here, as soon as I get here, gentlemen, what pipe set are we using here? We're using 200 mm. This place was supposed to be 125, remember? Here's supposed to be 125. Here's supposed to be 125. But due to minimum requirement, due to code requirements, I'm using 150. But the pipes here, I got the pipe from D is approximately 150. The pipe from F is approximately 200. Gentlemen, common sense will tell me by the time I go to point H, I've been using maybe 250, but let us do it and see how it goes. So when I get to point G, when I come to point H, sorry, if you look at it here, let me demonstrate this. Point H here, which is here, this is point H, is going to be the value of F plus the value of G plus its own value. So if I go to the chart, the value at H will be, its own value is 0.94. Yes, it's a small catchment. However, I'll add the value of 5.64 coming from catchment G and add the value of 23.49 coming from catchment F. And that total value will be what? 30 liters per second per hectare. I will now go to my design chart, go to 30 and read it off against 5%. It's still 200. It's still 200. So it means the maximum pipe size in this my network is 208 inches pipe. Okay, and that is it. Please let me pause this so we can ask question.
My question here is, I'm looking at catchment A, and you have the length of pipe going across to the end of that catchment A.
Yes.
And that pipe is 700 mm.
The diameter.
The diameter, and we've taken into cognizance the total contributing area in this section A to size it. So my question is the pipe going to be 700 from beginning till end, or will be at the end at near the junction between A and B? Where
it will be along the whole end, sir.
Is the whole
length? When you move
that,
to catchment B, catchment, another catchment that you can start changing, sir.
Okay.
Yeah, it will be the same, sir.
Okay.
No need to start changing it in between both ways. It's a safety thing. So it's the same. Yes, thank you. That's a good question. Now, can you see now that we have designed the size of the drain that can take up that frequency of rain? So if you now go to catchment B, gentlemen, the same thing applies. Catchment B has an hectare area of 5.47 hectares. You multiply it by the coefficient of runoff to get the effective contributing area or the effective impervious area. So out of 5.47, the area that we'll consider that will contribute to runoff or that is effectively contributing runoff is 2. We multiply that 2 by the rainfall intensity. It will give us 262. However, the discharge at B now is now the discharge coming from A plus the discharge at B. So the total discharge now becomes 9.88. Is that not common sense? Yeah, that should be common sense now. Look at it. A is discharging into B, right? So if here is 700, what will be B? So let's go to our chart. Or let's just go to the answer. So, oh, sorry. Sorry. Yeah. So at B becomes 900. The question I expect you to ask me is how do you get 900? Because this is 988, this is approximately 1,000. So if I go to my design chart and I go to 1,000 and I read it against 3%, because the slope at point this place is about 3%, it's giving me around 1,000. That's how we got it. So this is 1,000, and I read it against 3%. It's giving me something close to 900. So one of our things we'll do when we get back today is please study this chart. And I have more charts to send to you. Because if you go online, you see hundreds of them. I can bet you, if you are working in a place like Arup or all these big organizations, you can practically develop your own chart. Or you adopt one from one of these big universities, MIT, Harvard, or top-tier engineering schools. This one was developed by Institute of Sanitary Engineering, University of Stuttgart. There's a one I have. I'll send it to the group. It's developed by the United States Federal Highway, AASHTO. I'll send it to you. These are big organizations that are into research and development. They come up with their own charts. Most big consultancy companies develop, you know what I mean, something you use frequently now. Like they have charts, they have templates. So if they want you to design stormwater, they'll just give you their template. All you need to do is you just go there, impute your discharge at every point, and the result will just pop up. Yes, I can even do it, but then, you know, patronage is slow. And there's no provision for R&D. Okay, Engineer Hamza, what's your question?
Hello, well done, sir. Good afternoon.
Well done.
My question, thank you very much for the listening. My question is regarding the slope.
Yes.
So you mentioned we
are doing
slope
assumption, but now they use the real slope, sir. Look at how they use the real slope. Go ahead, still go ahead. Yes.
Okay, look, you know, in the beginning, you said 3 factors: the pipe roughness, the slope,
yes,
and yes. So the
by
slope.
these charts, by using these charts, we have fixed one. You know, these are 3 unknowns.
Yes.
So we need to fix 2 and look for 1. Go ahead.
Okay, so we are getting the slope from the surveyor. I just wanted to ask, as civil engineers or designers, are there any factors that affect how the surveyor, obviously the topo, are there any factors that? Okay, and then
it's just the topo. The difference between point A and point B, the difference in height divided by the length. Pythagoras.
Okay.
Tan theta.
So
opposite over adjacent, right?
Tan, yes. Yes.
I wish I can draw it, but I know you understand what I'm talking about.
Then the second thing is still, there's this, like, I don't know if it's a rule of thumb or it's appropriate thing to do. People
Go
just,
ahead.
when there's a design, there's a road design, then the slope is just referenced from the road when they are doing the pipes. When they are doing.
But that's the perfect way. That's the perfect way to do it.
Okay, it's actually right.
Of course,
not in layman's. Okay.
Yeah, it's perfect now.
Okay, so those are my.
They cut and fill. Yeah, that's the best way to take the slope. But that's what it is. And now watch now. They're walking along the road. Okay, from point 1 to point 2, which is usually less than 4. You know that the road, the average slope cannot be more than 6%. You're aware of that, right?
Yes.
Yeah, but I mean, you know what I mean. I mean, if it is possible for you to do your cut and fill, so it doesn't go above 6%. In pipe sizing all over the world, both for stormwater, the maximum slope the advised to use is 4%. I think I mentioned it in our last class. 4%. The maximum, most times, you try as much as possible to maintain 4%. If it's going above 4%, you might experience critical flow, supercritical flow, sorry, which most times leads to pipe erosion, leads to negative pressures. I mean, professionals have determined that try as much as possible. Like in road design too, 5-6% is like minimum safety. It's not like I can't do 9%, 10%, but I mean, cars can have issues. Except where the natural topography does not give you that flexibility. Then you don't have a choice. But if you have the choice, you have to cut until you achieve 6%. Are we together? That's what civil engineers anyway.
Okay, sir, I was wondering, do you have any experience designing any sewer system in Dutse, Jigawa State?
No, not at all.
Okay. I came across a situation where the designers were complaining that the topo of the area is too flat to get the slope they want. So I don't know if it's a lack of competency from themselves, or is it possible to be?
It's possible, sir. It's a flat land. It's a flat land, and it's very possible, sir, that what you need to do as a designer is that you play around with the slope. It could simply means maybe you dig more, or I don't know, flat lands can be quite difficult. The implication is that the minimum flow velocity in a sewer network is 0.5 meter per second. The complaint they are complaining is blockage. Their complaint they are complaining is blockage. You know why? Because it's not a pressure system, it's a gravity system. So if the land is too flat and there's no pressure to push it, then blockage is inevitable. So it simply means somehow they have to dig and provide some minimum slope. That means they have to dig inside. Can dig as high as deep as 2 meters in some places, unfortunately. And in some cases, the pipe might flow on the surface, maybe protected. Do you understand me, sir?
Yes, sir. Totally. Thank you, sir.
That's the complaint. The complaining is how the thing will flow because there's no pump. It's by gravity.
So come up with a solution.
You need to come up with a solution, or you find the route, the best route that will give you the slope. And guess what, sir? You know the best route? Streamline.
Sorry?
Streamline. Yes, natural streamline. In 90% of the cases, your sewer line should follow the river stretch by the side of the river. Because if that river is flowing, your sewer will flow, sir. That's a rule of thumb. That's an idea. In most cases, if you want to design sewer in a big city, find the stream and then give an offset to the stream and follow it. As long as that stream is not a lake, it's flowing, let your pipe follow it. That's why in most cases, you see that wastewater treatment plants are located close to streams, true or false. True. Even nuclear plants are always located close to the stream. The reason is for discharge, intake, and influent and effluent. That's the reason. Because at the end of the day, the effluent of the cooling tower, anyway, the water for the cooling tower, basically, and then the water for the cooling also come from the stream. The same thing applies to wastewater treatment plants. Wastewater treatment plants, in most cases, are always located on the banks of a river. The two reasons is that after treating the water, when you discharge it, you discharge it back into the stream. And then your pipe, ideally, should also follow the river bank because the river bank has a natural slope. So as long as, like I said, as long as the river is flowing, your pipe laid along the banks of that river is definitely going to flow. So I want you to start to observe it. Anywhere there's a treatment plant is always located along a particular river. In fact, even water treatment plant too. Because anyway, surface water treatment plant. Because the idea is that you take water from the upstream. You discharge it, spent of the treatment. Remember, treatment plant also produces wastewater. Now, either you treat it again and discharge it back upstream. So the treatment plant stays water, as the river is flowing, you build a dam upstream. You build a diverting structure, okay, a divert structure, take the water in, treat, pump 80-90% back to the city overhead tank, then 10%, which is now contaminated with suspended solids and product of treatment, which could be nitrogen depending on the treatment processes, which could be sludge. Basically, it's going to be sludge, suspended materials. You now treat it or you discharge it back into the river where they are depend on the regulation, depend on the city regulation. I don't even if that makes sense. I think it does.
Yes, sir.
Okay, so now we go back to catchment calculation. So here you see that catchment B has a pipe size of 900 mm pipe. Then let's go to catchment C. Anybody that knows catchment C will know that catchment C does not have upstream. Okay, so catchment C, the effective area is simply total area multiplied by the runoff coefficient. That will give you 5.22. Then 5.22, which is effective contributing area multiplied by the rainfall frequency, give you 6.58. Gentlemen, If I have gotten 6.58 and I have gotten 7.32 and I'm a lazy engineer, I will simply use the value for 7.32. I don't need to go and size anything. But then let's size, we can still go and size. Okay, in this case, because because its frequency, because the slope is not the same, I'm getting 800. But all of us know what 800 can do, 700 can do it. Difference in this case is that the slope is 5%. So it is smaller pipe size is achievable. Just like your Jigawa experience. Did you see that even though the discharge here is more, the pipe size was 700 because the slope, this is to tell you the impact of slope. The slope was 5%. Then in this case, even though the discharge is also close to 700, but because the slope is almost like a flat land, you need a bigger pipe size. So those Jigawa people, something they need to work on is to use bigger pipe sizes. So two impacts is that they will end up using big pipe sizes, which will impact their cost, and then they might have to dig in some cases, or the pipe need to flow on the surface in some cases. So that's the implication of having a flat land. Okay, so catchment D is now huge. Catchment D, even though it has a contributing area of 1.45 hectares, and its own flow is 182 liters per second, the total flow in catchment D, let's look at catchment D again. Catchment D is here. It's going to be B plus C plus itself. Are we together? Yes, we are. 182 plus 652, this will give us 1.846 liters per second. And the slope is 1 in 400, which is 0.25%. So going to the chart now, we're going to get a pipe size of 1.1 mm. Remember, this is a surface area, gentlemen. So at the end of the day, you can decide to use a different shape of pipe, but the surface area must remain. Are we together? This is for circular pipe. If you're using trapezoidal, you just make sure that the surface area is the same, equivalent to 11100 millimeter pipe, 1.1 millimeter pipe. Catchment E is not going to be a big deal. Catchment E is just normal 800 because catchment E is on its own. See, catchment E is on its own. 800 mm pipe will work. Okay, until you get to catchment F. Catchment F will now give you about 26800. Okay, and the equivalent pipe size is about 12 mm. And there's a caveat. The caveat says it is very critical and it's on the limit of our chart. So if I should get a value that's above this, I'm going to use empirical value. It means it has gone beyond rational method. It means has gone beyond rational method. It means I have to now do the calculation manually. Or if I'm a very smart engineer, I'll add an arbitrary value to this. Maybe increase it to 1.4 or 1.5 to take care of any excess. But the limit that this chart can design is a 1.2 mm diameter circular pipe. That's why we said that the rational method has a limit of 75 hectares to 100 hectares. Anything above that, rational method will not give you that required accuracy. So I give an assignment here. I say, what is the pipe size of catchment G? So catchment G is 4.06 hectares. The effective area will now become multiplied by the runoff coefficient, which is 5.22, and that will give us 6.57. So catchment G is simply the nominal pipe size of 800 mm. So in this case, any value that is 700, we just use the nominal value of 800 mm pipe, 0.8 meter pipe. You see how we get nominal values? So once I do calculation and I get nominal value, I even get something between 600 and 800, I'll just be using 800 mm pipe. That's why sometimes when I look for some design of engineers, you see them using the same pipe size, and I'll just be laughing. Yes, you can use mostly nominal values, but some critical areas, you can't just use nominal value. Especially if you're going towards a downstream, you must increase it. So catchment H is now 3.88, that's almost 3,000 meter cube per seconds. Gentlemen, you know what 3,000 meter cube per seconds? That is almost like a dam now. Outflow of a dam, speed basin of a dam, sorry. So that is quite critical. So we now said not applicable to our charts, but use empirical method. We say that the value should be around 1.4 to 1.5 mm pipe. So in essence, the rational method has its own limits. But as an engineer, you should know when the limit is there. And if I use the limit, look at it. If I now make an assumption of, say, the water will flow at 2 millimeter per second, and I say that Q is AV, and here Q is what? 1.33, and velocity is 2. That means the area will be what? 1.6 millimeter. So you can see the closeness of my assumption and empirical assumption, because this chart cannot help you. So you might have to look for a bigger chart. So this is what I want us to do when we get back. Please, in your find time and go through the Nigerian Code of Practice, check the whole cities and master what they are. Even though you have this value, you have this thing anyway. Whenever there's a problem, like the engineer from Jigawa, we're going to check. Well, no need. What else to check what the value is in Jigawa or city close to Jigawa. So I want us to study this catchment calculation for sewer and catchment calculation for stormwater. Please, that is the exercise on how we were able to calculate the rational method. Then study this chart also. So I've done it. So if you check all what we did, this is area impervious. You now multiply this by this, it will give you this. You now multiply by the rainfall frequency, it will give you this value. So look at those values we are getting. Here they are. Okay, so this is rainfall frequency, is the same all through. This is the time of flow. Don't mind all this 10.8, 10.5. It's just for academic purpose, just to tell you that at some point, the rainfall frequency, the time of travel is exceeding 10, but we can assume 10. Okay, and then for the frequency, as is exceeding 10, the frequency is also going towards out of 126. But all of us know that 126.3, the difference is not so, it's very minimal. Okay, any question? Did we get something today? Let me pause the training. Let me pause it. Okay, see if there's any question that will make